start, so please take your seats. So welcome again to our next AI/ML Conversations meetup here in New York City. We are very happy to see you, and thanks for coming. I see a lot of new and returning people here, so thanks for returning. It's very important for us. This means that we are moving into the right directions. And for the ones who are new here, for one who are new here, I'll remind the structure. We meet here every month at Capital One Flatiron. We invite two speakers to present, and we also have a connection in between them, as well as after hours writing at the bar a few blocks away from here. So we encourage you to sign up for speakers. We welcome speakers from all backgrounds, and if you love talking about AI, ML, can talk on hours, please use this form for Google Forms or reach out to us on LinkedIn after the event. Also join our Discord channel, where we post their information, openings, or just social. For ones who are from Superman, you can use this QR code. I'm not sure how that works. Please just scan it and you'll get some perks from there. This is the link for the bar. I'll show you after the event as well. And with that being said, I'm passing the board for Coin, who is from Capital One. He'll tell a little bit more about the great opportunities here.
Thank you, Brad. So I want to first thank Capital One for visas and hosting us here in this nice building. I work at Capital One, and Capital One is hiring, so we have a bunch of positions. If you are interested, just please come talk to me either during the break or after the second presentation, and I can give you an overview of the process of how Capital One goes about hiring if you're interested in becoming a Capital One employee. That's it. Any questions, just reach out to me.
Thanks, June. Thanks, Capital One. Glad to see you all. And I want to mention that here is harassment-free environment, and we take it seriously. If you're offended in any way, please come talk to me or other organizers you just saw. And we're going to have a couple of talks tonight. A scientist from MIT will tell us how they use ML for physics, and then we will discuss how we can go about fraud detection in a new reality where there are deepfakes and all other stuff, very scary. Looking forward to that one. And again, if you registered with Super Moses, you have another opportunity to check out this code. And I wanted to ask you, do you remember those times when we were saying machine learning instead of AI? I think those times has gone forever. And I want to invite our first speaker here, who's going to tell us about AI meta optics.
Let's see. So I'm going to invite you to the world of meta optics. Just out of curiosity, how many people have been related to Meta? I mean, the Facebook. How many? Okay, a couple of hands. Sorry, I have to disappoint you. I don't have any slides about Meta or the Facebook in here. So I guess most of you would have a question from. Okay, so this is my proposed outline for today's talk. Let's see how far we go through that. There are essentially like three parts. First one is to bring you to the world of meta optics, and the other two are related to how we can use AI tools. One is more like a conventional one, let's say convolutional neural nets and fully connected neural nets for forward design of the meta atoms, how to generate large pools of different geometries, like of nanostructures. And the second one is more interesting of how to bring Gen AI into inverse design problems. All right, so what is meta-optics? So it's actually, historically, it dates back to, interestingly, back to Soviet Union. In 1967, there was scientist Viktor Visalaga, and he was an experimentalist, but he came up with the idea. He's like, what if we have materials with like very unusual magnetic response or very unusual electrical response? Although those materials, they didn't exist in nature, and a lot of his colleagues just told him, come on, it's like nonsense. And your paper is, no one cares about this paper because it's unrealistic for what materials we have. Although in 2000s, we started to get more advanced nanotechnology tools, particularly the lithography. This was primarily powered by semiconductor industry, and the progress is still going on. Now we can still make structures down to below like 5, 10 nanometers. And so this is about, let's say, if we're talking about like the light and how it interacts with the matter. So matter is what was given to us by nature. But on the other side, we can also nano-engineer or create the structures, nanostructures, with the properties which go beyond what is given to us in nature. And here comes the Greek word meta. So that's what we call when the light interacts with this nano-engineered environments called meta-optics. Just one-on-one on electromagnetics, because I'm going to use a lot of terms from here. So I'm going to deal with the waves, with electric and magnetic waves. Here we mostly care about the electric fields. So like this Wi-Fi, the cell phones, you know, the wave propagates and its oscillations of the electric fields. In optics, these are the fields of oscillating at higher frequency. So each wave, even if you look at the waves in the sea, in the ocean, in the water, you know, there's like always like bumps, peaks and tops and bottoms. So the amplitude is how much it goes up and down, and phase is essentially like the state of the wave, whether it's the peak, whether it's the bottom, and some other positions along this wave. Essentially, phase is very important for interference and interaction of these two waves. Because the subject I'm going to talk about, we're going to consider like different sources, and then each of them kind of produces these waves, and all of them interfere with each other, and we can create or engineer the wavefront. Okay, so the wavelength is in the space, the distance, let's say peak to peak, in time. The time when it goes back and forth on cycle, this is the period, or if you inverse it, this is the frequency. Okay, and here I would like you to remember the words amplitude and phase. I'm going to use it a lot. So now, by mentioning these nanostructured materials, if we let the wave interact with the nanostructures aligned across the plane, each of them actually acts as the wave source, because it scatters the wave. You can think about it as a stone in the water. And here you can have like a superpositions of these sources and they can arbitrarily create the wavefront or create the wave you would like to have. Here I have a simulation, like some demonstration, that if you know the pattern which you prepared, and you know how each of these micro nanostructures scatters the field and where it's located, you can in principle have a lot of degrees of freedom to reconstruct the wavefront you want to have. And the first demonstration, which is the fundamental element in optics, is the lens. So you can either have it as the curved piece of glass. So essentially you can think about lens is the transformer of the wavefront. So you have a plane wavefront on one side, and when it goes through the lens, it becomes a spherical wave, so that it goes converges into the focal spot. And you can think about the lens as the distribution of the material, so that each pitch of this lens, it has like a different thickness, because if you move along the curvature, and then as a result, you kind of introduce phase at that specific location. But this is not the only way how you can create the lens. You can do it, for example, you can take a flat piece of glass and put these nanostructures. Of course, you need to know the response of each of those nanostructures. And you can recreate similarly the same effect as for the curved piece of glass. So the key advantages of this approach is that you have more degrees of freedom for optical engineers how to reconstruct the wavefronts. You can these devices have been shown to be much thinner than the traditional lenses where, for example, in the phone, you have to stack, like for wide-angle lenses, you have to stack 6 or 7 of them together in order to fight aberrations. Here you can go with just fewer components, even one. That's what we showed, that was at MIT. And the other leverage is that these lenses, they can be fabricated at a large scale using semiconductor facilities. So that could be a wafer level fabrication. They don't have to be like plastic molded, and then you have the CMOS chips, imagers, and then you have to align them and stack them together. Here you can produce wafers of those CMOS imagers, wafers of those optics, stack them together, and then dice it, and then you have an optical engine. And this field has already moved from the lab, so it started like from 2011. Some people say it's like even earlier, but the big boom started from 2010s, and then since then it has been emerging, and now it's moving to the startup. And I'm also now at MIT, our breakthrough was in the area of wide-angle lenses, like fisheye lenses. So we found a way how to make them smaller, and this is wide-angle, like hemispherical field of view and diffraction limited resolution. So why care? I think the killer applications for this lens, I'm not saying like we're completely replacing the existing lenses. There is a detail related to the frequency range. I think the best applications for this metal optics is the narrow bandwidth applications, where you either have like active illumination or like a very narrow bandwidth for imaging. So here, for example, I think it could be used for like in consumer electronics for 3D sensing, like depth sensing, computer vision, VR for eye tracking, gesture control, face recognition, and so on. All right, so that was my first overview of section number 1 about metal optics. I hope you got a grasp about what it is, where it stands, what are the main terms I'm going to use, and now I'm moving to some of the main problems we're having while, for example, designing this metal optical stuff. So the first thing I would like to bring you is to the design of the microstructures. So essentially, for like 2010 and even till now, a lot of people are still using commercial solvers. So this is a full wave electromagnetic solvers. What you do, you create a 3D domain with periodic boundary conditions, then you mesh it, it's a dense mesh, and then you solve differential equations in each of the nodes. In particular here, you solve maximum equations, and this process, it takes time. Here is an example. By the way, this is an illustration of like phase and amplitude. So here we put, for example, simple geometry like a cylinder in a narrow volume, and then you can have a look that this cylinder on the left, the cylinder on the right. Okay, this cylinder, left and right, seems like quite an mirror for myself. The thicker cylinder delays the wave more than the narrow one. So you can see, you can just count by the number of stripes. And here you can, at the top, like the color basically shows what is the phase delay. And so by varying the geometry, you can vary what is the phase delay of this nanostructure. The other thing we care about is the amplitude, like how much of the field goes through, like the transmittance. For optics, for lenses, the more field goes through, the better, because otherwise it works as an absorber, it's not efficient. And these are the two things we, first of all, like for very simple things, we really care about. And the main thing about this simulations that, as I said, it takes a lot of time. Well, depends what you call a lot, but 30 seconds per run. So, for example, if you are doing a multifunctional metal surface, you would need to generate about 100,000 different geometries, and it's going to take you about a month of running it on one computer. Of course, you can maybe send it in parallel, but at least for one node, it takes a lot of time. So the question is, can we bypass this direct electromagnetic simulator and instead use a neural net so that we're given as an input the geometry and the material parameters. In this specific case, this is a cylinder, so it has radius, thickness, gap, and the material it's made of, refractive index. And on the other side, we would fit it in the neural net, into the black box, and magically we can get the amplitude and phase responses. So we typically run it not for a single frequency, but we do like a frequency span. And that's the problem we're solving here. First thing you probably know is that this amplitude and phase functions are kind of nasty ones from the mathematical point of view, because they have very sharp transitions and these jumps which are related to the resonant conditions of these nanostructures. And essentially the first simple trick you can simplify the problem is to move from these like sharp functions to the smoother ones. And it's done by just doing the mathematical conversion. So instead of amplitude and phase, we translate them on the language of the complex transmission coefficients, and you can see right away the functions behave much better. It's easier to predict. For this machinery, we would first do like the training. Of course, it's a supervised type of machine learning on a fully connected layer network. So as an input, we have the geometry, and then it goes through a set of, here, for example, like 4 layers, and as an output, it produces the spectrum of the transmission coefficients. One of the network works for predicting the real part of this coefficient, and the other one imaginary, and the other one for imaginary part. And then you go through the mathematics, and you get the final result. So let's see how it works. This is an example of one of the runs after it's trained. We were able to get to the accuracy of 99% for both amplitude and phase. This has been trained on about 50,000 samples, and as the boost compared to direct electromagnetic simulations, it's about like 500 times. So instead of 30 seconds, we can do it in like 15 milliseconds, so which substantially decreases the time. So instead of a month, you can do it like easily within a day. So like even not a few hours. So that was cylinder. Are we really limiting ourselves by that geometry? No. Because we know that a cylinder has very few parameters, and as a result, by just varying this geometry, it would be difficult to get a good pool of these nanostructures. So we need to go to more complex geometries. I will explain it. I have a slide to show the difference, like when we move along the line of increasing the complexity of the geometry. So here we just increase the number of geometrical parameters for the top view. Instead of 1 in the previous case, now it's 4. Then we do similarly feed it into similar type of neural net and get, I think, outstanding results with accuracy below, with the error rate below 1%, like 99.5% accuracy, and also similarly boost of about 600 times faster results. So I already mentioned that we need to increase the complexity of geometry, but why? Why do we really need to do that? The reason is finding the microstructure is not the only challenge we have. The next challenge would be related when you make a device, you are going to make like a phase transformer. And you will start from mathematical like continuous function, which represents a phase, which is shown on the left side here. This is a simple example of the lens. And what you do after that, you're going to create a grid, and for each point of the grid, you're going to place this meta-atom or nanostructure. And you need to have a group of the nanostructures. It depends on the degree how you discretize this phase space. Usually we cut it into 8 pieces, which correspond to like 0, 45 degree, 90 degree, and so on, like till 316. So for that, you need to pick up not just the simple task is to find not a single good meta-atom, but a group of them, which will uniformly cover the whole phase space, and ideally with the best amplitude possible. So if we just take this H shape, and in this case the thickness was fixed, maybe not the best thickness, but with this particular shape, if we look at this polar diagram, which shows how uniform we can fill in the phase space for this later stage of building the optics, you see there is a gap. Like we don't cover the full circle. Ideally, we want to have the points on the outskirts, so where the amplitude is 1, and we want to have it along all the values of the phase. That would be the ideal case. Inside, we don't really care much because this amplitude, low amplitude means that the light doesn't go through, it's probably reflected back. Maybe you can use it in other types of devices if you're making a reflective one. But for the transmissive one, the best would be to have I have a point here, like the ring around. And to solve the problem, it's like in a general case, we can go to the freeform geometries, like release ourselves from the parameterizing geometry and just go to the images. So here's the approach. We can generate a bunch of these images and then try to see how well we will fill in whether we're going to have this uniform distribution. To do that, so for the images, we choose the format of 64 by 64 pixels. And the way they're generated, we're basically throwing these rectangular bars in one of the quadrants. We do it for one of the quadrants because we like to have it symmetrical. It's related to the fact that we like to have our optics polarization independent. Sure, there is also a direction where you can include polarization in this device, but in this example, no polarization involved. And then we can also vary the thickness, refractive index, lattice size. Since we're doing with the images, we would like to, the known way that the convolutional neural networks really do well with processing images. So before it goes to the fully connected neural net, which shortcuts the simulation, we do this multi-stage convolutions, and then after that it goes through and gives a prediction. So here I would like to show that by increasing the complexity of the geometry, we can actually substantially increase the quality of this pool of the nanostructures, and now we have like a really nice distribution, and we can easily pick up meta-atoms with a high quality and build optics with a high efficiency. And here I would like also not just to show you the design, but we did fabricate it, so this goes in parallel, like software design side as well as the fabrication. So here's an example. We have targeted making a lens which works at 2 different wavelengths. Here the situation is actually more complex than in previous cases. But for two of these wavelengths, the goal of the lens is that it collimates the beam, so that sometimes when the beam comes out of the fiber, there is like a lens at the end, but then after that you would like to send a parallel beam, and that's what this lens is doing. Essentially, it's the inverse of the imaging functionality. Just a few words so that you can appreciate the complexity of this particular case, because we're dealing here with two states for two different colors, so two different wavelengths. So the same physical device needs to have two phase maps, two phase profiles. And in order to do that, we need to have a pool of not 8 metaamps, but 8 squared ones. Because what each of them is doing, it switches between the two colors. So if you have 8 colors and you want to do all the switches between all these colors, so that will be a 64 metaamps to find. And we have done that following the same procedure. Here is a case which led to the fabrication. So this is the generation of the pool of the metaamps of freeform geometry, about like 80,000 of them, which has been done in 100 seconds instead of a month. And here there is a plot which shows a nice distribution. So it's not that dense, but we can still find the candidates and build a device. After that, we have a few filters because we need to find 64 metaamps out of the 80,000. And the way we do the search, it's a two-step search. On one side, we want to filter out and find the high-quality metaamps. So here we're focusing on this figure of merit, which is a combination of the two things. On one side, we want our nanostructures to be as transparent as possible. On the other side, we would like them to be to decrease the phase deviation, to remove the phase errors, because we're dealing with the interference, and if the antenna is slightly out of phase, it introduces errors to the wavefront, and then the device doesn't work as it should be. So we have found a few candidates, a few several groups, and then after that we do the fabrication test. So these metaamps are actually physically fabricated. Here you can see the scanning electron microscope, and we pick up the geometries which actually survive, and which has narrow enough sidewalls, and they can be resolved with the tools which are used in fabrication, specifically lithography and etching processes. And here we go. This is the photograph, the optical microscope of the fabricated structures. So this is the optical. This is the collimator, and here it shows the electron microscope. The zoomed in, you can actually see these nanostructures. We of course have done the analytical comparison. How does the structures we design, and how do they turn out? And from this example, it seems like there is a deviation about 10%, like 10 nanometers, and the corners are rounded and not as sharp as they here in the design. And if we try to predict with a full wave simulation, what is the intended performance, and what is the performance of this non-ideal metaamps if we just directly plug in the shape. And it turns out the deviation is not that bad. For 780 nanometers, it's almost negligible. For another wavelength, there is slight changes, like about the 5% in transmittance and the degree in terms of the phase error. And in the experimental test, we basically send a laser beam through the lens, which focuses it, and after that there is a metal lens, this is the collimator, which creates the parallel beam. And then we move the camera along the distance to find out how much this beam diverges. So, and here you can see that the beam actually does diverge. This is the real world, there's nothing perfect, but the divergence angle is good enough. It's less than 0.1 degree. Maybe I can have a small stop here for the questions for have like a one or two questions.
I have a question about the physics of the material. So can you manage through, I mean, basically passing electricity, the color perception of the people looking through this glass? So for example, I mean, I would assume that through the visible spectrum, the wavelengths are different for different colors. For example, can you like filter out like red, like orange? So like same as diving, like the deeper you go, you lose red, you lose orange, all the way till you lose blue. So can you like manage the color filtering? And another question would be, can you change the properties of the lens to basically zoom in, zoom out without losing colors? So like this is gonna be like important for business solutions. So like you don't want to lose colors. So that like two questions in one.
I see. Yeah, this is quite a complex task. But so about the filters, yes, it is possible to, as I showed, like you can engineer the behavior of these nanostructures, meta-atoms, depending on the wavelength. Actually, the best performance is done for single color or like a very narrow bandwidth. That's what, like in the company, we're targeting the applications which are narrow bandwidth. And in principle, you can design what happens to different colors. Like for example, RGB, you can have like different projections. You can, for example, since you have meta-atoms which are, for example, transparent at red, it could be absorbent at green. It depends, like if you have this nice library, you can tune it, what it absorbs, what it transmits. There is such a degree of freedom. About the zoom lens, here this is all like passive devices. So I think for zoom lens, you need some sort of activation. And that's what another work I've done at MIT. It's like on the topic of reconfigurable optics. I think that better fits it. And there we used a material which has a switchable property, so we can change the refractive index. And yes, we can change the zoom without like loss of losing like the color option. But that was done for a single wavelength.
Awesome. Any more questions?
Thank you. Are the simulations that you're kind of demonstrating here to simulate the actual physical device, is that similar to like the NVIDIA presentation on digital twins, or is that a concept that you're considering?
What kind of concept?
I think Jensen Huang was talking a lot about digital twins and simulating kind of machinery or physical phenomena in kind of virtual space with AI. So is that something that you're basically doing with this process, or is it a little different?
Yeah, it's similar as like inference. So this is the kind of bypassing the electromagnetics. So we can solve honestly the Maxwell equations, but maybe we don't have to solve if we have a trained neural net, because essentially it can find the roots how to build the relationship between the geometry and the electromagnetic response. So I think, yeah, it's like bypassing the physics. Yeah.
Still another question here?
So you're basically saying by implementing or experimenting AI with meta-optics, or trying to make the meta-optics thing more efficient?
Mm-hmm. Correct.
That is a game changer.
Yeah. It's like originally in the first years the efficiency of the lenses was about 1%, and now we're like pushing to the limits of about like 80-90%, and still trying to find the ways how we can make it better. It comes both from fabrication side, because the tools need to be precise in the designs, because some of the meta-atoms, there is another side that they need to be robust, so that if you slightly change the geometry, how much it would affect the electromagnetic response. So that's like another search which is done with this work. Another conversation how we can improve the efficiency. Yes, overall it's pushing the efficiency of optics.
I have a question regarding the intensity of light. I remember back in physics, when light penetrates lens, it drops by half the intensity. So I'm curious, when, let's say, the amplitude lands perfectly on the ring of the diagram that you showed, is that amplitude analogous to the incident light, the amplitude of the incident light, or is still dropping by a lot, assuming the ideal case? Or it's a physics question.
Yeah, so for the lens, typically what they introduce is anti-reflection coating. So it depends on the material, because interface between two materials can introduce back reflection. So that's why usually even like the glasses, the optics you have has this anti-reflection coatings. And then, what was the other thing you asked? Sorry, I forgot.
So even, let's say the amplitude of the...
Oh, amplitude, okay, for amplitude, yeah. Amplitude, basically it stands for how much of the light which is incident on the optics passes through. This is like the degree, that's exactly like 1 would be 100% close to. Yeah, okay. I can just maybe mention, I know you probably have been waiting for this fancy Gen AI approach, how we can use it here. I just have like a few slides. I hope many of you have heard about GAN, so this is Generative Adversarial Network. It's essentially a generator, like an artist, and the other one is a critique. They would compete with each other. And what they do, the generator tries to create the fake piece of art, and the critique tries to identify whether it's a true one or the fake one. And at the end, if the artist or the generator figures out a way how to really fake it, and the critique, the really strict critique doesn't catch it, means that the neural net can generate the designs which are very close to the ground truth. Here is just like a few trends, because what we're using is a long abbreviation from what is like original GAN, but basically a few features which is added here is it's like stabilized by gradient penalties, and then we use, of course, convolutions because we're dealing with images, and we feed in the spectral information, like the spectral response of the nanostructures as the conditions for the generator. Here's a diagram of how it works. So essentially, I'm solving here the reverse problem. We first give it what phase and amplitude we would like to have, and then ask the generator to give us the geometries. There can be many solutions, so the generator can maybe come up with like hundreds of solutions which could satisfy the same conditions. And the reverse problem is we're essentially like here sending the spectral responses, and it mixes them, concatenates them with the Gaussian noise, send it to the generator. Generator creates through this transposed convolution the fake images, and then both ground truth and fake images go to the discriminator. Discriminator does the convolution, then uses this, compares the two distributions for these images, and then gives the outputs. So there's like the loss functions for both of them, and then the tricky part is how to train both of them at the same time so they learn at the equal pace, because otherwise if critique is stricter than the generator, there's no way a generator can find a good solution and cannot really train, or the opposite way. And here's a demonstration that's in fact, we specify not the exact phase and amplitude, but we can give it the range. Let's say 90 plus minus 5 degrees, or plus minus 10 degrees, and then amplitude from 0.8 to 1 here, and then it can give you a set of the solutions, of 100 solutions here. It takes longer to train this net, like 72 hours instead of like 7 or 5 hours on the forward pass. Here is more statistical results that we can do it. We show here that we can do it for different amplitudes and different phases. You can see there is even statistical outlier, like the green one shown here. And another idea that this GAN approach can be used not only just for generating individual meta-atoms, but it can also generate the whole meta surface. Of course, you have a computational restrictions on how large, how many meta items in the array, but it is possible. In this case, we are designing, we are giving it a task to create this bifocal lens, and then it starts like from a complete noise, and then it slowly, after thousands of iterations, converges to the solution of the whole meta lens. Yeah, and here this was like a short demo of how to use GAN for inverse design problem, but the take-home message is so that meta optics is the new way how to create the optical devices, optical engines. The key advantages of it that we can push it to the higher performance because we have more degrees of freedom. It's also actually much faster for the optical engineers to do it because you have fewer components, small form factor, applications in like I think narrowband is primarily like a beachhead market. Of course, broadband would also eventually catch up. And then for AI tools, we can bypass the direct electromagnetic simulations, so which the design process is significantly faster, and also we can do it the opposite way using the Gen AIs.
Thank you. Wow, can't wait for a time when the lens will look like a lens and you probably only will be.
Yeah, I actually brought, you can.
Oh wow! Stop.
There's one of the first samples here. It's super flat, but it looks like something shiny and lens.
Yeah.
Probably need like a microscope to really appreciate its beauty.
Super cool. All right, we'll take a break for like 5 minutes. You can use this time to chat with Mikhail, and we'll return back with another great talk about using AI in KYC and fraud detection. Thank you.
Thank you.